In this work, we present a new disjoint compression algorithm for the odd-cycle transversal problem. An odd-cycle transversal, also known as OCT, is a set of vertices that has non-empty intersection with every odd-length cycle. In other words, if we remove an OCT, the resultant graph is bipartite. OCT is a well-studied problem in the parameterized complexity framework. There are three 3-par-K algorithms known for this problem. Here K is the size of the solution. Each of these algorithms employ the iterative compression technique. The key part in this technique is the disjoint compression subroutine. Given an OCT, find a smaller disjoint OCT. Each of these algorithms transform this problem into finding appropriate vertex separators. After nearly a decade, the bound for OCT was improved to 2.3146 par K using linear programming techniques and a reduction to vertex cover. We will now describe our approach to the OCT disjoint compression problem. Just to recall, the problem is given an OCT T, find a smaller disjoint OCT T prime, if one exists. Let us now use the reduction from OCT to vertex cover. We take 2 copies of the original graph and add edges between identical vertices. This graph has a special vertex cover. It contains both copies of T. Let's say T1 and T2 are the copies of T. There is a vertex cover for this new graph that contains T1 and T2. Further, this vertex cover also has the following property. For every vertex not in T, it has either the first copy or the second copy, but not both. This is the crucial property that we exploit in our algorithm. Now, the task of finding a smaller disjoint OCT is reduced to finding a vertex cover with this special property. The property is, for every vertex V in T, either V1 is in the vertex cover or V2 is in the vertex cover, but not both. Once we find such a vertex cover, T prime can be obtained easily. Just take those vertices of the vertex cover that have both their copies. The corresponding vertices in G is the required T prime. Let us now focus on obtaining such a special vertex cover. We require the vertex cover to have exactly one copy of every vertex in T. So we iterate over such vertex covers of the graph induced on T1 and T2 and try and extend it to a vertex cover of the whole graph. This extension is easy as the graph excluding T1 and T2 is bipartite and bipartite vertex cover is polynomial time solvable. Thus, if the graph G has an OCT that is smaller than T and also disjoint from it, at least one of the choices in the enumeration will find it. As a consequence of our disjoint compression algorithm, we have obtained a simple 3-par-K algorithm for OCT. The distinguishing feature in our iterative compression approach is that we iteratively reduce OCT to vertex cover and then compress. We do believe that our approach also has added to the growing understanding of the relationship between OCT and vertex cover.